Hello and welcome to our lesson on conservation of mass. This is for both foundation and higher tiers. Okay, so conservation, it means the amount stays the same. So you may have heard of conservation with regards to the environment, conserving resources, conserving the animal population, conserving trees, all that sort of thing. When you talk about sustainability, saving the planet by not destroying things. So conservation is about keeping things the same. And mass, well, when we think of mass, we think about the amount of matter or the amount of stuff that we have. And in chemistry, we're looking really at atomic mass or the atomic masses in a reaction. We're keeping the masses on the reactant side the same as the masses on the product side. So the law of conservation of mass states that in a reaction, mass is not created or destroyed, so it must stay the same. Let's have a look at an example here. Now this is a balanced symbol equation. I've got two magnesiums on the reactant side and I've got two magnesiums on the product side, so that has been conserved. And I've got two oxygens here on the reactant side and then two oxygens on the product side as well. So they have been conserved, the atoms are being conserved. And this is how conservation of mass works in a balanced symbol equation. You would have the same number of each type of atom on both sides of the equation. And that's conservation of mass. We can also look at the actual mass itself. So if I think about, okay, what's the mass of a magnesium atom? It's, well, let's round that to 24. And what's the mass of an oxygen atom? Well, let's round that to 16. Okay, so let's think about these numbers here. So if I add up those masses here, I've got two magnesiums, 24 each. I've got two oxygens, 16 each. Add them all up, and on this side of the reactant equation, my reactants add up to a total mass of 80. And I'm saying 80, not 80 grams, because it's a relative atomic mass or relative formula mass in this example. On the product side then, I've got two magnesiums and I've got two oxygens again. So again, my relative formula mass here is 80 again. So in both ways then, either looking at the atoms themselves, the number of atoms of each type are the same on both sides of the equation, conservation of mass, or I could look at the mass itself, conservation of mass. So as a rule then, the same mass on both sides of the equation, mass is conserved. This only works if your equation is balanced, because if you haven't balanced it, you're going to have the wrong numbers on both sides. Okay, so if you look at this equation here, do you think it shows the conservation of mass? Well, hopefully you would say no. It doesn't show conservation of mass. I don't have the same number of atoms on both sides of the equation. I've got two copper here and only one copper here. I've got two oxygens here and only one oxygen here. Now so this is obviously an unbalanced equation. The easiest thing to do would be to put a 2 there, making that now balanced, showing conservation of mass. Okay, so does this show conservation of mass? Okay, well I've got two lithium here and I've got 2 times the lithium there, so that's okay. I've got two fluorines here and 2 times the 1F there. I've got 2 fluorines here. So yes, this does show the law of conservation of mass. So what would you predict in this situation here? I've got 50 grams of water plus 10 grams of salt. How much do you think the mass of my salt water will be? Well, if we follow the law of conservation of mass, that number would be 60 grams, wouldn't it? Because the law of conservation of mass states that we cannot create or destroy mass. So if I had 50 plus 10 to start off with, I'm going to have 50 plus 10 to finish off with as well. So it's going to be 60. How could you test that prediction? Well, you put it on weighing scales and take the measurements before and after. Okay, so what might it look like here then? So I've got an equation here, magnesium plus oxygen making magnesium oxide. What's the missing number going to be? Well, if I've got a total of 15 grams on my reactant side, that's my mass on the reactant side, 10 plus 5, I'm also going to have 15 grams on my product side. So my missing number there is 15. Now that might be phrased something like this in an exam question. If Harry heats up 10 grams of magnesium with 5 grams of oxygen in a crucible, what is the mass of magnesium oxide made? Okay, and you do that equation and you figure out the missing number. Okay, let's look at this equation. This time we have magnesium plus oxygen. We know our magnesium. We don't know our oxygen, but we know we've got 16 grams of magnesium oxide. Well, if I've got 16 grams as a product, I must have had 16 grams as part of the reactant, so my missing number must be 6 because 10 plus 6 makes a 16. What would the question look like? Well, it might be something like this. Harry heated up 10 grams of magnesium in a crucible until it had all reacted. When he measured the total mass of magnesium oxide, it was 16 grams. What was the mass of oxygen? Okay, and there you go. You're just, again, writing out that equation, filling in the numbers you've got and seeing what you're missing. Now, don't worry about a crucible. I'll come back to that in just a few minutes. So let's look at an exam question. Why don't you pause the video and have a go at this for yourselves and then come back to me. Okay, so first of all, a pharmaceutical company is one that makes drugs and medicines and does that sort of research in industry. So if you're not familiar with the word, that's what it means. Okay, so there's lots of information going on here. I suggest bugging the question. So my first command word here is calculate, and I'm calculating the mass of the aspirin. Okay, so I'm looking for the mass of the aspirin she makes. Now, where does it mention aspirin in this question? Well, it mentions it here. Aspirin is a painkiller used to treat headaches and reduce fevers. Well, that's not much help. It's just kind of informing me what we're doing. It mentions aspirin in the equation. I think that equation is going to be really useful. Okay, and then what else does it mention? It says use the principle of conservation of mass. Okay, which we know is in a reaction, mass is not created or destroyed. Okay, so I'm trying to find this aspirin in the equation, the mass. I know that if I've got a certain amount of reactants, I'm going to make a certain amount of product as well. So do I have some other information? Well, I've got lots and lots of numbers here. I've got 6.9 grams of salicylic acid. I've got 5.1 grams of ethanoic anhydride, and I've got 3 grams of ethanoic acid, plus there's some aspirin, which is the one I'm trying to find out. Now, I've run out of space on my diagram here, so I'm just going to write it out here. What number am I missing? You can see where I've got those numbers from. So let's look at my reactants. 6.9 added to the 5.1 gives me 12 grams in total on the reactant side. So I must have 12 grams in total on the product side. I've got 3 grams of ethanoic acid. Well, that means I must have 9 grams of aspirin because 9 plus 3 makes the 12. Okay, so pause the video and have a go at this question for me, please. Okay, so hydrogen peroxide solution breaks down to make water and oxygen. I've got an equation there. I'm probably going to use it. In an experiment, 6.8 grams of hydrogen peroxide makes 3.2 grams of oxygen. Okay, so I've got some numbers there. Use the principle of conservation of mass to predict the mass of water made. Okay, well, let's look at these numbers here. I'm just going to input them underneath the equation. So I've got 6.8 grams of hydrogen peroxide making the 3.2 grams of oxygen. And the question is, what's the value of that water? Well, if I have 6.8 grams to start off with, conservation of mass states I must have 6.8 grams to finish off with as my products. So 6.8 minus the 3.2 gives you 3.6 grams. Okay, so the next question then, what is the mass of oxygen that can be made from 680 grams of hydrogen peroxide? Now, on the surface of this is a bit of a weird question. Where's this come from? Well, it's recognising that here, that is 100 times bigger than 6.8 grams. Well, if that's 100 times bigger, it would make sense that that's also 100 times bigger. And so the mass of oxygen you would get is 320 grams. Sneaky, eh? In reality, even though the law of conservation of mass states that we cannot create or destroy atoms or mass, in reality, when we do a practical or an investigation and we measure the mass, it often changes. It's often not the same. So you've got 3 choices really. Either your mass will stay the same, or it will increase, or it will decrease. Now, if it stays the same, that's what we expect because We're not creating any atoms, we're not destroying any atoms, we're not creating mass or destroying mass. So there's nothing going on, no extra atoms involved at all. Now, if you increase mass, it must mean, because you can't create atoms, you've not magically created atoms that didn't exist in the first place. You must have gained atoms from somewhere else. They've come from somewhere else. They already existed and you have taken them. Now, this is likely to be something like oxygen from the air. If you're burning in oxygen, that oxygen becomes part of the compound you're now measuring. Now, if your mass decreases, it means you've lost some atoms. So they're still there, they're just not on the equipment that you're using to measure. They've managed to escape. So let's look at some examples of this. Okay, so let's look at this one here. This is a really common practical you will have done at some point. Here's the crucible I was talking about. It's this little white bowl with a white porcelain lid on it to stop any gases escaping, in theory anyway. Now, realistically, what happens in here is you have got your magnesium, a piece of magnesium ribbon, you put it in your crucible and you heat it up, okay? And you kind of remove your lid, you lift it up a little bit, allow the oxygen to get in because you are burning the magnesium in oxygen. And when you do this experiment, you would expect the law of conservation of mass would stay the same. In reality, your mass would increase. And that means that you've gained atoms from somewhere else. So they already existed, you haven't created any atoms, but they've come from somewhere else. Now in reality, that's going to be the oxygen. So here's the equation, magnesium burning in oxygen to make the magnesium oxide. So you've got this added oxygen, and every oxygen atom has a very small mass, and so it does add up and you can measure it. Okay, so here's another example here. So you've got your top pan balance here, and what they're doing is they've got some hydrochloric acid and some marble chips, so small pieces of marble rock. They call them chips for some reason. You can see their equation below. The calcium carbonate is your marble and the hydrochloric acid. Okay, in this reaction, usually what you find is that your mass would decrease. And this means that you've lost some atoms. So again, you've not destroyed them, you've just let them escape and you're no longer measuring them on the top pan balance. They're no longer there, they've managed to run away from you. If you look at the equation, the answer, or there's an obvious reason there. You're making carbon dioxide gas. And so it's escaping, it's a gas, and it's going to go up. Now, what they've tried to do to avoid this, and this is another question they might ask you, is how do you prevent this from happening? And so what you can do is put that cotton wool at the top of the conical flask or a rubber bung, something that's going to stop the gas from escaping and trap it. So that's one way of doing it, and another way would be something like this, where you can trap the gas in another liquid and you'd have to measure that also. But a rubber bung usually does the job. So here's a classic neutralization reaction. I've got hydrochloric acid, HCl, and I've got sodium hydroxide. There's the alkali, NaOH, and it makes water and sodium chloride. And here's the top hand balance with the two liquids in it. Now in this sort of equation, you would probably find that mass would stay the same, which means we've got no extra atoms, we've not gained anything, we've not lost anything, nothing's escaped. And if you look at the equation, you can see why there's no gases there, you're making two liquids. You had two liquids, you've made two liquids, so there's no opportunity for any atoms to escape, and you're going to be measuring the full amount. So you would expect the mass to stay the same. Okay, so let's have a look at this exam question. Pause the video and have a go for yourself, please. Okay, so let's book this question. It says, look at the word equation, calculate and explain. So look at the word equation, calculate the decrease in mass and explain why the mass decreases. Okay, well, let's look at this here. We've got a decrease of 0.88 grams. And why is it decreasing? Well, if I look here, I have a gas, and that's why the gas was made and it's escaped. Okay, nice and easy. That's the end of today's lesson, guys. Thanks very much.